In section 4.7, we're going to start to talk about how we can use the ideas of what we've learned about computing derivatives to help kind of solve some problems. We're going to be interested in optimizing certain quantities. So this might be something like, maybe if I consider that I have a company, maybe I'm interested in optimizing or maximizing the profit that this company can make over the next year. Maybe I'm interested in minimizing the amount of cost that it takes this company to produce something. I could also maybe think about, maybe I'm interested in minimizing the amount of time it takes to complete a given task. Or I want to maximize maybe the number of points that I could earn on an assignment. So these are the sorts of questions that we're going to be working with. How do I maximize or minimize different values? And so you can maybe start to see how this is immediately going to relate to the ideas of finding maximums and minimums of given functions, which is what we've been working on for the past several sections. So here are going to be some general guidelines for optimization problems. Now, in every problem, we're going to be doing each of these 7 things, even though it doesn't seem like we might actually talk about them directly. But the first 2 are really going to be the most important ideas. To be successful in these questions, we're going to really try to make sure that first we understand the scenario. If we don't understand the scenario at hand, it's going to be really, really difficult to successfully answer the question. And to help in understanding, we're going to try to draw a diagram. Now, of course, we're also going to have to go ahead and introduce some different symbols, label our diagrams, think about how we want to label different portions so they're easy to remember and talk about. And then we're going to have to ultimately determine what thing in this question we want to maximize or minimize. We're going to want to try to write a formula for that. And then we're going to go ahead and use our ideas of derivatives to help us try to find where this maximum and minimum might occur. Now, again, we're not going to list out these steps in every problem, but you'll see me kind of progress through them in some of the videos to come. Now, in addition to that box of guidelines, we also have here a box of important formulas. Now, these are formulas that you should really be aware of because they're going to be very common things that we're going to use throughout this section in different questions. So things like volumes of boxes, spheres, cylinders, cones are formulas that we should really know or at least start to dedicate to memory. Surface areas are maybe some new ones. Surface areas for a box, for a cylinder, and a cone should also be very, very important. We should also know formulas for different areas, like areas of triangles and rectangles and things of that sort, as well as circumference and diameter. Now, we'll be able to go back and take a look at these formulas, obviously, as we work through questions in this particular section. But when it comes to homeworks or exams and being efficient, not having to look these things up is going to be obviously very, very important. So let's take a look here at the following theorem, which will actually be really, really crucial for completing step 7 in the optimization guidelines. Well, this theorem right here is kind of an adaptation of the first derivative test that we had back in a previous section. What this really says here is suppose that c, again this is some x value, is a critical number of a continuous function, which is defined on some interval. Now here's an important idea. If it's the case that my first derivative is positive every time I have x values less than c, but the first derivative ends up being negative for every single value that is less than c, that is, if I could imagine drawing out a number line that looked like this, if c was a critical value, and everywhere below c I have the graph going up, and everywhere after it I have the graph going down, well then automatically I should be able to see that, yeah, c corresponds to an absolute max. That's what number 1 here is stating. Notice though that number 2 is going to be stating that if I'm working with this value of c, and for all values of x that are less than c, my derivative is negative, and for all values after c, my derivative is positive, that's going to allow me to produce a minimum. But notice that if this is working for every single possible value of x, right? So all values of x to the left are going down. All values of x to the left make the derivative go up. Then that's going to signify that this isn't just a minimum, but it's actually the absolute minimum on the graph. So an example of this would be something like, maybe like a function of a parabola, right? Something like this, where I can see that this bottom point is definitely going to be an absolute minimum for the entire picture, because every item every y value on the left side is obviously larger, and every value on the right side is larger. That is, my slopes of my tangent lines are negative and then all positive. So this idea is really, really crucial. If I only find a single critical value on a function, and I find that it corresponds to a max or a min, then that should actually be the absolute max or the absolute min of the function. So this is really, really, really nice. Of course, this requires that I actually am still able to go through then and double check whether my function is increasing or decreasing using my derivatives. And so we'll start to go ahead and see how we can implement this idea as we look at example 1 in the next video.